there. All right, tonight, looking at a thing called a chi-square test of variance and an f-test for variance. Previously, what we've been looking at are testing of means and the difference between the averages of scores. But tonight we're going to look at a testing of variance and seeing if there's a significant difference in the variability of two data sets. So the topic we're going to look at is the test of variance. We're going to look at this chi-square test of variance, which is testing a one sample to an established norm. Now that should sound a little bit familiar because we did the one sample z-test and the one sample t-test, which is testing the means of one sample to an established norm. This one is testing the variance of a sample to an established norm. And we're going to look at this thing called an f-test, which is testing two independent groups for variability. Then something that's more so on the lines of mathematics is this thing called interpolation. Now, understand that the computer, a statistical process computer, will calculate all this stuff for you. But when you start looking up critical values on charts, as you may have to do somewhere down the line, you may not see the exact number that you have. Remember called the degrees of freedom? You may not be able to find the exact degrees of freedom. In other words, if you have 16, and on the chart it's somewhere between 15 and 20, you have to make a decision on how to come up with that critical value. Now there's a rule of thumb we'll get to, and then there's a thing called interpolation that will more specifically identify what the critical value is. So we're going to be talking about that. So in the one sample z-test and one sample t-test, we were concerned with means, the averages of a sample to an established norm. But what if we're concerned about variability, or how scores are dispersed throughout a distribution and not the means? How scores, in this case, or the means, are centralized in a distribution. So in a lot of cases in manufacturing, there is a big concern about the variability of a data set. So for this type of measurement, we're going to utilize a technique known as a chi-square test of variance, where the procedure is used to test the variability of one sample, which is the observed, to an established norm or a hypothesized norm of variability. The other type of variance test is a test of variance between two independent groups. And we start looking at that, and this one we're going to refer to it as an f-test. Now we've already talked about a situation of what an f-test is going to be, but in this context we're going to be looking at f-test as the test for variability, and later on it's going to be used as the minor hypothesis when used as the independent t-test in the one-way analysis of variance. So it's known for the homogeneous variability between two independent groups, and is also known as that minor hypothesis that we've talked about. Variance signifies the magnitude of dispersion of a data set. In other words, how data is dispersed throughout a data set. We talked about in the initial chapters that it determines the height of a distribution. So as the variability is small, then it pushes the distribution upward to a more leptokurtic shape. If the variability is huge, then it's going to pull the distribution flat, known as the platykurtic distribution. And if it's just right, then we have this mesokurtic, or the bell shape that we all come to know and love. So why do we want to test for variance? It's an important factor to control, to have a picture of how groups, scores, items, etc. are homogeneous or alike, or heterogeneous or different. So we look at, in the variability, is when you have homogeneity of variance, the variability of the groups are very similar. When you violate homogeneity of variance, then they're extremely different. So in a manufacturing realm, when you start looking at variability on a production line, you want the least possible variability throughout the day, because if you have that small variability, that means the production product that you're producing is falling within specifications. When you have a variability that kind of wanders up and down, that means that some product is exceeding the specs, or some products are not coming up to specs, or very small. So when you look at this case, in this situation, Bruce Engineering is setting up production lines to manufacture a revolutionary cup. Okay? Well, in that cup, lids must be produced to fit that cup. Now, imagine, and a lot of people do, when you drink a cup of coffee, you stop in at some of these mom and pop gas stations, you get a cup of coffee and you grab a lid. Imagine if it came from a line that had huge variability. So at some point, you grab a lid, it won't fit the cup. You'll grab a lid that fits the cup, and you'll grab a lid that fits too loosely on the cup. If it fits too loosely, what you do is when you take a drink, then the lid comes off, the coffee spills all over you, and you become, fairly upset. If you get a lid that's too small, you try to force the lid on the cup, and you squish the cup, and the coffee falls all over your hand, which makes you upset as well. So you want a lid that fits nice and tight, and when you hear this, you know that lid is fitting soundly on that cup. So in a production sense, you want to have a production line that has very small variability, so this lid doesn't have this expansion of too large or too small. It falls within a very confined area, so you know that you're going to get a nice tight-fitting lid. So that's why in this situation you're going to be concerned about variability. The company is willing to accept some variation in the diameter of each cup, but the diameter cannot have too much variation, or else the lids will not fit properly or snugly. Now, this was an actual company years ago that all this data came from. So the question becomes, how much variability is considered too much? Well, that's what we want to look at in the production sense. So in this example, the company is producing 8-ounce cups, and these cups must conform to the industrial norm of 2.985 inches in diameter, all right, with a plus or minus variance of 10 thousandths. Okay, that's a standard norm. All right, at that particular time, in this size of cup, 2.985 inches, the variability can't be more than 10 thousandths. All right, now that's not a whole lot. All right. Because if you're looking at more than 10 thousandths, then you're getting a larger lid. If you're looking at smaller, you're getting a smaller lid. So it's very, good for a company to make sure they fall within these specifications. So as you do your production line, you are comparing what you have to the industrial norm. All right. So one group, one sample, to an established norm, which we're going to use the chi-square test of variance. Too much variability, plus or minus, and the lids will fit loosely or not at all. And we don't want that. I've been in a lot of situations on the road at wee hours of the morning and stopping in trying to get a cup of coffee and can't find a lid that will fit the cup. And you don't want to drive down with a cup of coffee that's hot with no lid on it. Or especially one that it fits on there, and then you take a sip and the force of the coffee just spills all over you at 2 o'clock in the morning. Right? So 20 randomly selected cups are selected from 2 separate pilot runs, and the following diameters were logged. Right? So here we go. Is this the right, here are the diameters of the cup. Here's the diameters of the cup. So we have a lid, and the lid has got to fit this cup. So in this sense, we're producing cups that fit a certain lid. So the variability of that cup now can't be too large or small, or the lid won't fit it. It's a state-of-the-art lid. So we want it to make sure it fits the cup. All right, so here's the diameter. All right, so in our 7-step process, we have the variance equals 10,000, or the variance does not equal 10,000. So all we're concerned about here is the difference. Do we conform to the established norm, or do we not? Okay, that's the question that we're looking at. So if the null hypothesis is rejected, it would indicate that there is a significant variation in production line. That's not good. In this case, we want to accept the null hypothesis because what we're saying is that there's no difference between our production line and the established norm. That's a good thing. If we reject the null hypothesis in favor of the alternative, what we find out now is that there is a significant difference and our line is producing too much variability when compared to the established norm. So if we fail to reject, the variability will fall within an accepted range. The variance symbol is used for hypothesis instead of the mean because we are testing variability and not an average. Step 2, alpha level, 0.05. Step 3, sampling distribution, because we have 20 in our sample. And a chi-square statistic, we need to utilize the corresponding distribution, and it's called the chi-square distribution. So when you look up into your tables, you're going to be looking up a chi-square distribution. And so the degrees of freedom is found by n minus 1, so we have 20 minus 1, or 19. So our distribution is chi-square sub 19. Our decision rule, we've got to locate the critical value. We've got to go back to that chi-square chart. The chart's divided into an upper end and a lower end. Now what you're going to find, because it's a chi-square, you're going to be looking at a situation where the distribution is going to be a positively skewed distribution. All right? That's a chi-square. Now, because of the name chi-square, there are going to be no negative numbers. Why? Because no matter what you have, you're going to square the value. So if you have negative, it's going to be squared, it's going to be positive. So there are no negative numbers. So the low end of the distribution is going to be 0, and the upper end is going to be, wherever it goes to. So the upper end, the lower distribution, is going to be 0.99. The lower end at 0.01 at the upper end. We're only testing a difference, so it's a two-tailed test. And we've got to be concerned with both ends of the distribution, even though it's all positive. So we're going to have an upper level, and we're going to have an upper level and a lower end critical value, even though they're both going to be positive. So we still have 2.5% at the upper end and 97.5% at the lower end, since our percentages must equal 100 or 1. So we have an alpha level of 0.05. We have to divide it by 2, so we're going to have 2.5% up here, and we're going to have 99.7% at the other end of the distribution. So the problem is now on this chi-square, in our search for our critical value, we find that 0.025 lies between 0.02 and 0.05. So we don't have an exact number for 0.25. Therefore, the largest critical value of these two with degrees of freedom of 19 would be selected, and it would be 33.687. I'll show you that in just a second. So the rule of thumb is when a value falls between, you take the larger of the two critical values. Now, there's a penalty to that, and I'll show you what it is. Also, at 0.97 lies between 0.95 and 0.98. Therefore, the largest critical value would be 10.117. So again, we don't find 0.975 anywhere. It falls between these two. This is this process called interpolation that I'll show you at the end. So for this example, I'm going to use this interpolated value. And as we finish, I'll go through the interpolation and show you how it came about. So the interpolated value for 0.025 is going to be 8.826 versus 10.117. Okay? Because the rule of thumb is you take the larger of the two critical values. But when you interpolate the value, you come up with a more precise critical value of 8.826. And for 0.975, it's going to be 33.095 versus 33.687. So we're going to talk about this as we go across. Now here's the chi-square chart, the chi-square table. Notice at the lower end and the upper end of the distribution. So the critical value of 0.975 falls between these two numbers here, 0.98 and 0.95. So we start looking at 19, we're going to find that it's going to fall somewhere between 8.567 and 10.117. The rule of thumb is, if you want to do the quick and dirty method, is you take the larger of the two critical values, which is 10.117. But remember, we interpolated that value to be a little more precise and a little more close over here. The other one, 0.025, falls between 0.02 and 0.05, and at degrees of freedom 19, it's going to fall somewhere between 30.114 and 33.687. And so we've also interpolated that value as well, because the largest of the two critical values is the 33.687. So that's the two that we have. So we look on our chart, we can see at the upper end, the larger of the two critical values is 33.687, but the interpolated value is 33.095. On the lower end, up here, you see the larger of the two critical values is 10.117 versus the interpolated value of 8.826. Now, this will be significant as we move forward with this. All right, so our decision rule is we're going to reject the null hypothesis if chi-square observed falls at or beyond chi-square critical of 33.095. That's the interpolated value. Okay? Or if chi-square observed falls at or below chi-square critical of 8.826. That's the interpolated value. Otherwise, we will fail to reject. All right, let's go back and look. 8.826 versus 10.117. 33.095 versus 33.687. All right? We don't need to use the absolute value signs even as we use a two-tailed test, because we're using chi-square values and the values are squared, so it's going to give us a positive number anyway. So the calculation, the formula for the chi-square test is pretty much straightforward. It's the total number minus 1 times the variance of E over the variance of O, where E is the expected or the calculated variance of the sample, and O is the observed or the standard value of which we're comparing it to. So in our formula, or in our data set, we look at our variance. Our calculated variance is going to be 0.0000486. And so as we run it through the numbers, we have 20 minus 1, or 19, times our calculated versus the standard, the national norm, okay? And we run it through the numbers and we find a chi-square value of 9.23, okay? 9.23. So summary, since chi-square observed of 9.23 does not fall at or beyond chi-square critical of 33.095, and does not fall at or below chi-square critical of 8.826, we therefore fail to reject the null hypothesis. So when we go back and look at our chart, 9.23, let me get the chart here, 9.23 at 19 does not fall below this, the number here, and so we fail to reject the null hypothesis. All right? Go back to where it is now. All right, so 9.23 does not fall there. So our conclusion is, since we failed to reject the null hypothesis, we conclude that the variability in cup diameter is accepted when compared to the industrial norm. So notice that 9.23 does not fall below the 8.826. Okay, it falls in the fail to reject region. Now, here's the punishment. Here's the problem. We failed to reject with the interpolated value, but what would have happened if we used the quick and dirty estimation method? All right, so the punishment is by taking the largest of the critical values. At each end, our critical values would have been 33.687 and 10.117. And so the chi-square observed of 9.23 would have been less than the critical value of 10.117, and we would have therefore rejected the null hypothesis. Type 1 error. because we chose the larger of the two critical values instead of the interpolated, more accurate value, we would have falsely rejected a null hypothesis that was true. And it could possibly cost Bruce Engineering a lot of money, because now, since the variability in this, by using the quick and dirty method, would have said you have too much variability, they would have made unnecessary modifications to their production line versus having taken the time and using the interpolated method and failing to reject, which is the more accurate and more true statement. So the punishment by using the quick and dirty method of just taking the larger critical value could have committed a typo and error and could have been extremely costly for Bruce Engineering. So now the problem, what they want to look at is, what if Bruce Engineering suspected that the diameter of the cup in the pilot runs exceeded the industrial norm? All right, so we have no difference, but what if it's exceeded? So here we go. Remember, the direction of the arrow in the alternative hypothesis points to the direction of the table of interest. So we're looking at succeeding, and then change the null hypothesis to less than or equal to cover all mathematical possibilities. Step 2, alpha is still 0.05. Sampling distribution is still x sub 19, or chi-square sub 19. And since we are testing a direction, and that direction is greater than the value which would be at the upper end of the distribution. So, referring to the chi-square chart, we must first locate 0.05 with degrees of freedom 19 and establish a critical value of 30.114. So if we look on our chart now, we do have the 0.05. So we don't have to guess, and we don't have to interpolate. So we look at the degrees of freedom at 19, and we find out that indeed the critical value is going to be 30.144. All right. Rejection of the null hypothesis. Anything exceeds 30.144. So our decision rule, we're going to reject the null hypothesis if chi-square observed falls at or beyond chi-square critical of 30.144. Otherwise, we're going to fail to reject. Calculation, we've already calculated the chi-square value to be 9.23, so we can proceed to the next step, which is step 6. Since chi-square observed of 9.23 does not fall at or beyond chi-square critical of 30.144, we therefore fail to reject the null hypothesis. So we know that the diameter now, in conclusion, and you see the rejection, the 9.23 falls into the fail to reject region. So our conclusion is, since we failed to reject the null hypothesis, we conclude that the diameter of the sample cups does not exceed the industrial norm. So with that, we know that they're going to be equal to or less than, and more so because of the variability, it's going to be more equal to than less than. So we go through this process now of one sample to an established norm. But what if Bruce Engineering, with their state-of-the-art technology, wanted to test their pilot line against another manufacturer using a conventional technology? So in this case, Bruce Engineering has a state-of-the-art line. And they want to compare that to an industry who uses a conventional, traditional type of way of producing cups and lids. So their idea is that if they can demonstrate a very good, tight control of variability, it would go a long way of selling machinery to other places. So we're not concerned with an established norm, but with a comparison of two independent groups and with unknown variances. The diameter of the 8-ounce cups manufactured by the state-of-the-art production line and a competitor's conventional production line. So we want to check the variability between the state-of-the-art line and the conventional production line. So a variance comparison between two independent groups is handled by a statistical procedure called that F-test. Or, as we move forward, it's going to be called the minor hypothesis, or a test of homogeneity of variance. Procedure, the Hartley's test. It's also called the Hartley's test for homogeneity of variance. It's a very simple calculation. It's the larger variance divided by the smaller variance. Okay? Not too difficult. Not too difficult. The smallest calculated value will equal 1, and only if the null hypothesis is true, and if the null hypothesis is false, the value would be greater than 1. Okay? So now, a unique aspect with this procedure is that the critical region is non-directional, two-tailed test. It's always at the right or positive end of that distribution. So, with that in mind, here's the data set that we already accumulated with Bruce Engineering's cups. Now we've taken a competitor's cup, we've gone to the different mom and pop stores, and we've collected a random sample of the competitor's cups, and we've taken the measure of the diameter of their cups, and we're going to see, is there a significant difference between the two? So in this case, we do the variance 1 equal variance 2, no difference, and the alternative is the variance 1 does not equal variance 2. This is the one that we want to see. Okay? Remember, the other one we didn't want to see any significant difference because that means you were against the industrial norm. This one we want to see a significant difference because it demonstrates a clear difference between the variability of the state-of-the-art line and a conventional line. If we didn't show any difference and we failed to reject the null hypothesis, it would be very difficult for Bruce Engineering to say and sell this machinery to another organization or business and spend a lot of money when they can still use the conventional method. So that's what we want to look at. So the variance of group 1 equal to the variance of group 2. If the null hypothesis is not rejected, we can conclude that the variances of the two groups are equal, which is bad news for Bruce Engineering. All right, step 2, alpha level 0.05. Step 3, sampling distribution. To find the appropriate sampling distribution, locate two values, a numerator and a denominator. So we're going to use the F-test table, or the F table in the back of the book. And we're going to look at the first group is going to be the numerator. The second group is going to be the denominator. The numerator represents the degrees of freedom in -1 for group 1. The denominator represents the degrees of freedom in -1 for group 2. Degrees of freedom of group 1 would be 19 because it's n minus 1. So we had 20 in the sample. So 20 minus 1 is 19. And the degrees of freedom for group 2 would also be 19 because we have 20 in that sample as well. So our sampling distribution is going to be F sub 19, 19. So the numerator and the denominator are going to be both the same, 19. So we have to locate those components on the F distribution. So we have to find the table that has 19 at the numerator and also 19 on the denominator. So we have to flip through the different pages until we find it. So our sampling distribution F sub 19, 19, we got to go across the top row and then down the column to find those. So here's our F table. Notice it's going to be table 5.3 where we're going to find somewhere up here 19 and also somewhere down here 19. But notice again, we don't have 19 in the numerator. It's somewhere between 15 and 20. So again, the rule of thumb is we take the larger of the two critical values, and at 19 down here at 0.05, at 19 at 0.05, we're going to take the larger of the two critical values, which is going to be 2.23 versus 2.16. So we don't have that in the numerator. We have to go through the whole process of interpolation, and we select the largest of the critical values and may inflict undue punishment to our summary of type 1 error, as we indicated earlier. So we're going to be looking at the critical values in the study will be the interpolated value of 2.174 versus what the larger of the two critical values, which would be 2.23. So we know that 19 is going to fall, or the critical value for 19 is going to fall somewhere between 2.16 and 2.23. Interpolating that value, it comes out to 2.174. So our decision rule in this case is going to be reject the null hypothesis if the F observed value falls at or beyond the F critical of 2.174, which is the interpolated value. Otherwise, we're going to fail to reject. All right, so there's our rejection region, our critical value, 2.174. Anything that falls to the right of that, we're going to reject the null hypothesis. Step 5, calculation, larger variance divided by the smaller variance. So group 1 has a variance of 0.000486. Group 2 has a variance of 0.0254,721. So when we start running all the totals, we get a value of 524.10. Right, since F observed of 524.10 falls at or beyond F critical of 2.174, again, it doesn't matter how far it is, it can be 1 million. It exceeded the critical value, so therefore we reject the null hypothesis. Please remember that there's no such thing as highly significant, greatly significant, hugely significant, almost significant, not nearly significant. There's only one choice, or two choices. It either is significant or it is not. There are people saying, well, wow, 524.10 versus 2.174, that must be highly significant. No, it isn't. It's just significant. That's all it is. All right? And so it doesn't matter how far out it goes. It falls into the rejection region, therefore it becomes a significant variable. Step 7, since we rejected null hypothesis, we conclude that the variance in the diameter of the cups between Bruce Engineering and their competition is not equal, so there's no homogeneity of variance, which is good news. So we know that there's a significant difference now in the variability of the state-of-the-art method versus the contemporary method, or the old style method. The chi-square distribution contains the following characteristics. Degrees of freedom equals an n minus 1. Chi-square approaches infinity. It takes on the characteristics of normality, even though it's a chi-square distribution. Chi-square distribution is positively skewed. The minimum value for the lower limit equals 0 because that's as low as you can go in a squared value, while the maximum value for the upper limit exceeds to infinity. The average of the chi-square distribution is equal to the degrees of freedom, and the variance of the chi-square distribution is equal to twice the degrees of freedom. And then finally, the chi-square test of variance is used to test the variance of one sample to an established norm. The F-test, which we just went through, the hypothesis is basically set for a non-directional two-tailed test. Even though we perform a non-directional two-tailed test, we have only one critical region, the upper end of the F distribution. Degrees of freedom is the n-1 for group 1, which becomes the numerator, n-1 for group 2, which becomes the denominator. The F-test is extremely sensitive to non-normality, especially when sample sizes are unequal, because we talked before about the pooling of the variability. So when you try to compare variance of one group that has a larger number to a variance of a group with a smaller number, it becomes very unequal, and the credibility and believability of those results are in question. The F-test is also referred to as the minor hypothesis because it's conducted prior to an independent t-test, analysis of variance, or multivariate analysis of variance, to make a determination of whether the data comes from population of equal variances. If you violate that homogeneity variance assumption, then that particular test, t-test, one-way analysis of variance, multivariate analysis of variance, may not be the appropriate test to use. You might have to get a larger sample size and try again. The F-test is used when the variances of two or more independent groups come into play. All right. Now, we talked about this thing of interpolation. We just completed a thing of the importance of variability and making sure that the variability of one group is equal to the variability of another group for the homogeneity of variance, but we also showed the importance of when you have a state-of-the-art versus a method versus a traditional method, that the variability control of those two would be extremely important. So as a company coming out with the state-of-the-art, they want to sell the machinery to other businesses, so it's very critical to control that variability. But this thing that we talked about, referred to as this interpolation. The rule of thumb being when you have, when it falls between two numbers, how do you know what that number is? And the rule of thumb, again, is take the larger of the two critical values, which we demonstrated earlier, committed a type 1 error, could have caused a huge upset in the production facility and an unnecessary cost. So interpolation involves the process by which we locate an area in question and its position relative to the highest and lowest value. So if you recall, when we saw a value of 0.025, we didn't find that value. It was between 0.02 and 0.05. So interpolating would find its exact location between those two numbers. All right? So then we subtract the largest critical value from the smallest and multiply that value with our position value, and then we either add or subtract our calculated value with the largest critical value in the range. Well, that's pretty simple. I just told you exactly how to do it. Now words are fun. Let's see how it is. Let's go back to the chi-square example where our alpha level was 0.05 in a two-tailed test. So that means we had to divide it equally on each end. So we had 0.25 at the upper end of the distribution and 0.975 at the lower end of the distribution. So we got to calculate the critical values in the range of alpha levels on either side. So when we looked at our chart, if you remember, 0.025 fell between 0.02 and 0.05. Okay? So the critical value is going to fall somewhere in there as well. So we've got to determine its location relative to the upper and lower value. So in this case, at 0.02 and 0.05, we've determined its location to be 1, 2, 3, 4, 5 thirtieths of the way between the two values, okay? 1, 2, 3, 4, its location of 0.025, and there's 30 values here, so its location is 5 thirtieths of the way between those two, the upper and lower end. All right? So you count the distance between the two. We've got to have our location value, so we can use the following formula. So here it is, our location value times the largest critical value minus the smallest critical value plus or minus the larger or smaller critical value depending on which way you're going. So let's put this in more things. We transform our location value from a fraction to a decimal. All right, so 5 thirtieths of the way is 1/6, or decimally, or in a decimal point, it's 0.167. So that's the first thing we have to do is transform that location value into a decimal, which we did, 0.167. Now we substitute the values in that formula. So we have our location value, which is 0.167, times the largest critical value minus the smallest critical value of the two, and then plus or minus the larger, in this case, critical value, because we need to subtract it. And so we have 0.167 times that all the way down the line, and we come up with the critical value decreases from 0.02 to 0.05. So 0.02 is 33.687, and it decreases down to 30.144. So we have to subtract that, 33.687, and subtract the value of 0.592, gives us now our interpolated value of 33.095. So we follow the same procedure on the other end of the distribution. So in this case, we need to find 0.975, and 0.975 comes 25 thirtieths of the way. So if we count the 30 data points here, we find that from 0.950 to 0.980, that 0.975 falls 25 thirtieths of the way in that distribution from the largest to the smallest. So we find 25 thirtieths, we have to change it to a decimal, and that's going to give us 0.833. We run it through the same formula. Our critical value is going to be 10.117 for 0.95 and 8.567 for 0.98. So we plug the values into the formula. 1.219 plus or minus 10.7, and since it decreases, we must subtract it, and that's how we get our interpolated value of 8.826 versus taking larger of the two critical values. So interpolation, when you go through this, it more precisely pinpoints where the location of that value lies between two points. All right, in the F distribution, remember we had the denominator, but we had the 19, but we didn't have the numerator. So the numerator fell between 15 and 20 because our degrees of freedom was 19. So now we look at our location value in this. We're going to see that 19 is located at a distance 4/5 of the way between 15 and 20. So we have 1, 2, 3, 4/5 of the way between that. The critical value between the two at degrees of freedom 15 is going to be 2.23. The degrees of freedom for 2.16 is going to be, is the critical value is going to be 2.16 at degrees of freedom 20. And so our interpolated value is going to be 0.056 plus or minus the 2.23, which gives us the interpolated value of 2.174. So by doing that, what you've done is now more precisely identify the critical value instead of taking the larger of the two critical values. So in this case, what we've done in this section, we've talked about the difference of variability, the importance of taking the one sample to an established norm. We've talked about the two independent groups, or the F test, because that's going to be critical as we run the minor hypothesis or the homogeneity of variance test down the road. And we talked about this thing of interpolation. Now, the computer will do that for you, but if somewhere along the line you have to look up the critical value by hand and you see the two, you can always refer back to the textbook and go step by step on how to make the interpolated value to come up with the more precise critical value to give you a much better indication of either rejecting or failing to reject the null hypothesis and avoiding a type 1 error.